So, it says an industrial facility has a waste tank. So, one of the things, problem statements are big, it does not mean problem is big, it is just you have to understand, gather information from this problem and fit it into whatever framework we are using. So, we have an industrial facility has a waste tank 20, I have given you dimensions, contains small amount of solid sludge. Solid sludge means it is water plus solids, a mixture of inorganic and organic components. A sludge occupies about 1 meter of the tank, okay, uniformly spread across. That imagine like a mud, if you dump mud into a tank, what it will occupy the bottom some region. The moisture content of the sludge is 0.4. The percentage of organic carbon in the sludge was estimated as something 15% dry basis, which is 0.15. Chemical analysis of the sludge showed a loading of 250 milligrams per kilogram dry solids on a particular hazardous of a particular chemical A, some chemical A. The mass of wet sludge is 600,000 kilograms. So, I have given you the volume, I have given you mass, which means you can calculate few things from this information. Sometimes you have to, when I design the problem, I just give some numbers. When you do the calculation, sometimes the numbers are inconsistent. They will, it will violate mass balance. In those cases, you correct it. If you have enough, otherwise you tell me, I will correct it. Okay. So, that is the basic idea, right. Now, what I have given is during a rain event, when rain falls into this, it mixes, it becomes a slurry becomes a suspension with addition of rainwater. The overall resultant slurry occupies 3 meters. Now, originally it was 1 meter and 3 meters. So, 2 meters of height is water, extra water that is added. It is like adding water and mixing, stirring up this thing, and the contents are then allowed to settle again. So, in the process of this mixing, what do you expect is happening? So, I initially have, so let me write down this problem in terms of the this thing. So, I have a tank which of initially I have some sludge, let us say I have some sludge, and the sludge occupies, I am saying it occupies 1 meter height and some cross sectional area. Now, I add water, rainwater, and so this becomes the entire thing becomes a slurry. Okay, so this is a physical description of the problem. Then after settling down, what we expect is this again, but now the top portion is not sorry. This is what I expect. Initially I add rainwater, this is a very this is also a suspension. So, what has happened between stage, this is, let us call it as stage 1, stage 2 and stage 3. In these 3 stages, this is what is described in the problem. What has happened in these 3 cases? First, there is certain amount of A is there here, all the A is contained here. When you add rainwater and you mix it, everything is mixing, the water and the solids are mixing together, and now what we have is we have A here and here, both here. A has now distributed itself into the water and this thing. Okay. What I am saying is I am then taking out this water out of this. Okay. All this water is taken out for analysis. I am trying to analyze what is here. So, this water is now taken out, and the sludge is remaining like this. So, sludge remains as it is. What I have also given in the problem is that this contains 10% of the organic carbon originally which was there in the sludge. It has now removed 10% of that organic carbon from there. So, this is the setup of the problem. Okay. Anybody has a doubt, question about this, how this happens? Now, very simple question that I am asking is, what is the expected concentration of A in the true aqueous phase here in this one? Yeah. What has happened is you have had rainwater, it is mixed with the, it has suspended, resuspended all the sludge, and it has caused contamination of water, and the water is being drained out, and this water is now, we were trying to find out what is there in the water, how much of A is there in the water. So, we do a mass balance in which of these systems? For true aqueous phase, on which of these 1, 2 or 3, which one will you do a mass balance on now? Huh? 3, 1, all of them are the same, they all have the same thing, but what is we are doing mass balance at equilibrium, initial and equilibrium. Yeah. So, we are doing it at 3. But we can also, it is 2 and 3 are equivalent in some sense. You keep mixing it, it is really 2 because that is the state of equilibrium. Then you wait for a long time for it to settle down, and we are assuming that there is equilibrium and this equilibrium is attained between these two stages, and it stays there, nothing else is happening. So, we are also assuming that nothing is going out, no evaporation. Is that what I have assuming 0 evaporation, no evaporation. So, in a real case scenario you will not see that, in a real scenario it will not come to equilibrium because it will evaporate. Okay. So, no evaporation, where our system is only this, only the slurry, water and the solid. So, the mass balance that you will write will be in terms of so what will be the mass balance? It will be before equilibrium, after equilibrium. Okay. So, what is it before equilibrium? Where is the A? We are doing mass balance for component A. Where is the A? We are going to write algebraic expressions. You do the calculations on your own. Huh? In the sludge. So, how will you express it? All the mass of A. So, mass of A in sludge. So, mass of A in water equals after equilibrium in water. Now, we are saying rainwater, now we make assumptions here. One assumption that we make here is rainwater contains no A. This need not be true, okay. Rainwater can contain some things depending on where it is, how it is being processed, because it is in contact with particulate matter. So, that is a complicated problem. Sometimes rainwater will bring what is called as wet deposition. Whatever is the particulate matter in the atmosphere, it will all be dumped into your, it will come with the rain, okay. So, it may add pollution to your existing system, where it is clean, it may add more stuff into that. So, a lot of what that is called as wet deposition. Our assumption is that we are not considering wet deposition, there is no A, that is simple. You can add all these complicated cases if you have enough information about the system, that is all. You can do it later if you know how to work this, which means that this is 0, okay. We are not, right now we are saying no evaporation. So, if you have evaporation, we will do that problem later in the.
Evaporation means evaporation of water or evaporation of air?
Both, but right now our concern is only water, the A now. So, evaporation of water occurs, then a lot of other things will change. So, those are complexities that the system will have subsequently. So, we are now only trying to understand the process of estimating the solute, but water also will change, can evaporate. So, we are modeling water and air evaporation separately. So, now it is mass of A in the sludge. What is mass of A in sludge? This one. How will algebraically, how will you define it? This is 0, this is the only thing that is before equilibrium, all the A is in the sludge. How do you express concentration of A in sludge, solid sludge? Using WA 3 into M3 equals, at equilibrium it will be WA3 star M3 plus into V2. This is the mass balance, very simple, similar to what we did in class for the other one. Only difference here is now we are changing, we are not adding pure chemical or anything, it is already there in the system, it is redistributing because there is additional water that is added. Now you have to, this is known, you will call it as WA30, which is given, this is given to you, this and this we do not know. So, we have to calculate M3 and V2. Yeah. This constitutes the biggest effort in the problems like this, Calculating of V2 and M3 is the main, is a little bit of, it involves a little bit of work. So, here what we have already is we have given mass of, what is given is mass of wet solids. So, you have to understand one thing, whenever we say M3, and in previous classes we have discussed, M3 is usually dry, this WA3 is on the basis of dry. So, you look at that, the definition that is given is the loading of 250 milligrams per kilogram dry solid. So, WA3 is always on dry basis, which means by that definition M3 is dry solids. It is a very hassle free way of doing it, because dry solids are always there, nothing will happen to them. The moisture content may go, and in this case moisture content is changing. You are adding water and removing water and all those things is being done. So, in those cases our mass balance is simple by we are keeping track of it by way of M3 only. So, mass of wet solids is M3 plus M2. Now, the M2 this particular we will call it as M2 dash, because this M2 is the pore water. In other words, we can also you can write your this thing as I can remove this and say it is M2 of 3, because it is the water mass associated with the solid. Yeah, and what is given M2 of the wet solid mass is given as 600,000 kilograms. Yeah. what is also given is the I have not given some information. I think you need mass second is given 4, theta is given 0.4, which means m3 divided by m3 plus m23 is given as 4. Sorry, m2. So, now I have volume of 2 is meter cube. Total volume is 20 by 20 by 1, which is 400 meter cubed. Total volume of 1 meter height of the sludge, total volume of the sludge at this point is 400 meter cubed. So, M3 is 360,000 kilograms, that is the balance that is remaining in this. So, for now we do not need anything else, this is we can do the problem using this, but in some cases you need to calculate the reverse is, if the moisture content is not given or anything, you need to estimate water content. So, you need the volume occupied by the solids, which means I need particle density of solids. From mass I will calculate particle density, using particle density calculate volume of solids V3 and then use whatever is balance volume occupied by. For example, in soils you have water and air, and if you have water volume occupied by soil solid plus volume occupied by water plus volume occupied by air, all of these constitute the full volume in the system. So, water saturated systems are much easier to handle this way. So, we have this and this, okay. So, now we do the mass balance, we have 250, let us go to the next page, WA3 0 M3 equals WA3 star M3 plus rho A2 star V2. We have 250 milligrams per kilogram dry multiplied by 360 kilogram equals, now here I will write now WA3 star by rho A2 star equals KOC FOC. So, therefore, this will become WA3 star becomes KOC FOC into rho A2 star. This is my equation for now. Okay. What is this? This is the concentration of A in the aqueous phase, true aqueous phase. Now, the slurry also contains what is mentioned in the problem, the slurry also contains 10% of the organic carbon. Organic carbon is a solid phase in the suspension, but that is not water, it is still solid, okay. There is chemical still sitting on it, and all that will come under this term, it is still part of the solid. Only thing we are saying is that is why we said that when we say we want to consider, we are considering this one rather than 3. they are the same, 2 and 3 are the same, except that equilibrium has happened and just the solids have settled down. We are still assuming that organic carbon is still there. So, we are not changing the system, we are not changing the equilibrium of the system or anything, okay. Everything is there as it is, no evaporation, no water is removed, nothing is added to it. So, the concentration of rho A2 that is present in this state should be the same here before settling and after settling, as long as equilibrium has been achieved. If you keep it stirred long enough for it to come to equilibrium, whatever the concentration that is there when in the suspended state will still be retained when you are settling all the solids out. This is usually the as long as you do not have anything else in the system, you do not add more carbon or you do not evaporate anything else, you are not disturbing the equilibrium. So, we are in our problem we are assuming that to be true. So, this rho A2 star is the true aqueous phase. Sorry, this is no, the other way, M3 is here, V2 is here, into KOC, KOC in the problem is 10, so this 10 raised to 10. So, KOC in is 10 raised to 1 meter cube per kilogram. This log KOC is 10 raised to 4 liter per kilogram. So, therefore, this is 10 here. FOC is 0.15, yeah, 10 into 0.15 plus 240 meter cube. This is meter cube per kilogram. So, kilogram get cancelled, milligrams. So, your aqueous phase concentration will be in milligrams per meter cubed, whatever you are getting. So, you can calculate that, this whatever this value is. Okay. So, you can see that lot of it is still in the, if you look at the magnitudes of this number versus this number, you can see that lot of it is still in the solids. The water it will shift towards the water if the water volume becomes very large, very large. If I take this and add, so if the order of magnitude of this for example is 3.6 into 10 raised to almost 5 multiplied by 1.5. So, the order of magnitude is 10 raised to 5 and this is 240. For this to significantly distribute itself into the water, you need to have a lot of water. You keep adding more water and more water, then the water then increases its capacity. The capacity to take chemical in the water becomes higher and higher. Okay. So, it also depends on the value of KOC. If the KOC is small, log KOC is 1, this number will become very small, this number will become small. So, the distribution of the chemical between the two phases, this phase and this phase depends on the volume of water as well as the KOC and the mass of sediment and all that. So, this mass balance is very clear. So, you can see where which direction the problem will go if I increase volumes of water or if I decrease certain other numbers and so on. So, you calculate the number here. Okay. Part B relates to analysis, chemical analysis. So, when we say true aqueous phase, there is a reason for when we call it as true aqueous phase, okay, and it relates to part B. So, in part B, suppose what I am saying is I have this case where I have this is 2 meter cubed, not 2 meter cubed, whatever this there is additional water now. So, there is some additional, so sorry I have mistake, none of you pointed it out. Yeah, rainwater, yeah. How much is rainwater? So, yeah, so this is not 240, this is huge. Yeah. This is of the pore water, V2 rainwater is 20 by 20 by 2, this is 800 meter cubed. So, therefore, the total V is 10040, this is bigger than this. So, therefore, this one. So, but what we are doing is now after separation we are taking out that 800 and going back into a different chamber. We are retaining the original pore water, we are letting it settle down to its original capacity, and we are pulling out all the 800 into here, into the in the next one. This is 800 meter cubed of rho A2 star, but it also contains 10% of the organic carbon that was originally there in the other one. Now here we are still not exposed it to water. Now here is where I am exposing it to air and I am asking what will be the transfer there. Now there will be a shift in equilibrium. Again we are redoing the equilibrium here because we are now exposing it to air. Okay. So the organic carbon is here. The organic carbon has nothing to do with evaporation because equilibrium has already been achieved, and this organic carbon that is there here has already participated in that equilibrium. If you add new organic carbon into this system, it will re-equilibrate, but as long as you are not adding anything new, nothing will happen. What are you adding now here? The problem that says I have a sample from this volume, I am taking a small sample, let us say I am taking a small sample of water into a glass bottle, 1 liter glass bottle with a head space of 200 ml. What I am doing is I am taking a 1 liter bottle, I am collecting the 800 ml of water and 200 ml air. This term head space is used in analysis, chemical analysis. Head space means this is the head space, this is called head space. If you take a bottle, you do not fill it up fully and you close it, there is some region that is on top of the liquid that is called as head space. We make use of this in chemical analysis, we will discuss that in next section. So, it is capped, it is closed, it is a closed container. Now, you can imagine what will happen in the system. This contains rho A2 star plus some organic carbon. Some fraction of the organic carbon is there in this, okay, little bit of organic carbon is there in this, and this contains air. So, the sample is extracted, now here is the kicker here. So, I am extracting, I am adding extract with hexane, which means I am doing this. So, what do I need to do to extract with hexane this sample? I have to open the bottle. When I open the bottle, what has happened? What will happen? Because there is head space, some amount of the A that is in the water has gone partitioned into air, and that will escape, that will go away essentially. Okay. So, what we are saying is when you have head space, there is mass transfer into air, into the head space, and therefore, there is loss of analyte from water. How much of analyte loss is there in the water, which means that the original concentration is rho A2 here. What will be the concentration there? It is a very simple calculation, it is a mass balance again. The original mass balance is again V2 rho A2 equals V2 rho A2 plus V1 rho A1 star. This rho A2 is the rho A2 star from the previous problem. Okay. Now, rho A1 star by rho A2 star is Henry's constant, which means that we have rho A1 star equals H rho A2 star. Rho A2 star into V2 plus H into V1. This is your concentration. Now, what has happened is, because the denominator, if HV1 this is 0, it will be the same, because now we have some volume of air and some Henry's constant that is acting on it. This denominator is greater than V2, therefore, you will get a small decrease in the concentration as compared to rho A2. So, rho A2 initial, whatever is going into the system, into the sample, the original true aqueous sample. Okay. This is all imaginary problem. Okay. None of these things will happen in real life.
So this time we need not to consider that organic process.
We will come to that. Here no, the organic, the organic, when you are talking about evaporation, where is evaporation occurring from? Evaporation occurs only from water. Henry's constant relates true aqueous phase to vapor phase. Particulate matter is all under a different equilibrium. Now, if I keep the water exposed to continuously to air, then evaporation is occurring and the water will deplete, and then there is a change in the equilibrium between the aqueous phase and the organic carbon. Then desorption will happen, all that will happen. So, we will talk about it later. For right now, the organic carbon is just a passive observer. It has nothing to do, it does not participate in evaporation yet in this equilibrium this thing. You can write, if you want, equilibrium for all the three. Okay, it is correct. It is a full valid way of doing it. I am ignoring it because I won't expect to see a big change, but you have to write the correct way of doing this will be MOC multiplied by W, we will call it as M3 WA3 plus M3 WA3, but this A3 is only organic carbons. So, a whole bunch of calculations you have to do. The amount of organic carbon you are taking in 1 liter is very, very small. So, we are now essentially neglecting that portion. Any big change is happening here, but you are right, that is the correct way of doing it. There will be a very small change in that, very likely. But just to make this point, that because you have head space, because you have allowed volume of air and with a significant H. So, this again, this number here depends on the magnitude of Henry's constant. Henry's constant is big, you expect this number to be big, or the volume of air to be big, similar to what we did in the rainwater and the sludge case, right. So, you will get some change. The answer is, do you expect any change? Answer is yes, because some amount of chemical will now partition into air. How much? That depends on the value of Henry's constant and the air, volume of air, and it may not be significant at all. You may see that the value is 2.4 and the other value is 2.399. So, it's insignificant. That is the call you have to make, whether it is relevant or not. So, you can also look at the magnitude of HV1 and V2. If you think it is, if V2 is much larger than HV1, you ignore this term and move on, assume that to be true. But be assured that for different volumes it may matter. So, this is an illustration of the losses that we were talking about in the case of chemical analysis in the last class. Now, second part of that question, yeah, the question is, if I extract with hexane and I will get, so what will I get when I extract with hexane? So, I take this sample, water sample, which is this, extraction, which will mean that I am adding a little bit of hexane. Yeah, and so all the A is now gone to hexane, and this hexane I am taking into a smaller vial and then transferring it to some instrument, analytical instrument, and I will get data. I will get a concentration of a mass of A that corresponds to this volume. So, I can get a concentration of A in this. So, mass of A from the instrument analyzed by the instrument using the calibration graph and all that, then the volume of liquid I am taking the sample from, the entire sample, I can get a concentration. This will give me a concentration. My question is, will this number which is measured, will it be the same as the rho A2 true aqueous phase that you estimated in part 1? Why not? One of you is shaking your head. Why not?
It is not possible to extract complete amount.
Let us assume we have done all that. Let us assume we have done all calling. Assuming recovery is 100%, we have, that is a different issue. Assuming recovery is 100%, I know, or assuming I have calculated recovery. My question is very different. Question is this rho A2 represent the rho A2 that you estimated in your calculation?
Still no, sir, because some amount escaped into air.
All that is accounted for.
Organic phase.
Huh?
That organic part
So, what does the organic part do?
also has some concentration data.
Yeah.
Also linked.
So, what you are measuring is the hexane, is you are extracting everything. You are extracting this rho A2 measured includes the aqueous phase plus the organic phase. It is a significant amount of organic chemical is sitting on the organic phase, right. The KOC is very large, 10% of the original organic phase is still a large amount. So, it is very likely that you will see a large concentration if you take the entire water sample as it is and extract it against the concentration you have estimated based on the calculation true aqueous phase. Okay. So, how do you correct for this experimentally? Huh? You can filter. One is filter the OC before hexane extraction. Sometimes this is very difficult to do. Okay. So, the other option is to
Subtract this value.
measure the OC and then correct using the mass balance, same mass balance. Now, this mass balance will be whatever value you have now got corresponds to both the phases. You have to distribute it. You will say this is the total amount of mass that is contained in this volume equals volume of water plus whatever is there. So, correct for true aqueous phase. By doing this, so we have rho A2 measured multiplied by volume, total volume equals rho A2 true aqueous phase multiplied by volume plus W8 OC multiplied by mass of OC.
Every time during extraction the concentration, the compound A gets extracted even from the carbon or even from the solid.
It will if you do not separate it. It depends on what your objective is again. If your objective is to estimate evaporation and all that, evaporation will not occur from the carbon, it will occur mainly from the aqueous phase only. So, your estimate will go a little bit off, but if you do not care, if you say as it is the water, I just want to know how much is there. So, for example, if this water, somebody is supplying this water for drinking, you are drinking everything, right, your intake contains everything. So, then you may not want to correct for it, you may want to actually measure what is the total concentration here along with, well, organic carbon you can't see sometimes. The water sample it will look very almost clear, but it may contain organic carbon, very small amount. So, what the in terms of if you are not having a filtration mechanism before drinking water, whatever is if I am unable to filter my water, I would like to measure the concentration of that, which including the organic carbon also. If I am ingesting the organic carbon also from a risk assessment point of view, that is also important, I need to know that. But if I am doing calculations like this, if evaporation and mass transfer calculations, you are interested in the true phase, true aqueous phase, this will give you a wrong estimate of that. So again we come back to this question of what is the objective of your analysis. So all of these are right and all of these are, you have to use it in the correct spirit of how you want to do this calculation. The third part, any questions on this? Every step you do mass balance, that is all, simple. You just have to understand, is there a, so a problem I am giving here is very artificial, it never happens almost like this, because we are never at equilibrium in most of the systems. We are always in some state of unsteady state, something is happening all the time. It is very difficult, very rarely do we get equilibrium in environmental systems. So you need to understand the purpose of having equilibrium, why is it useful, we discussed that a few classes ago. So the third part C is something that we did last Thursday and Friday in the surrogate analysis. So we do not have time for it, we will do it tomorrow, we will work on that problem tomorrow. And question number 2, I think this we did it last class, I think the illustration of a minimum detection limit and all that, we did this. So question number 2, the minimum water sample required, we did this in class, illustration of sampling volume and all that. Minimum detection limit was used, so you already know that. Question number 3, soil with moisture content of 10%, wet basis and considered as wet is measured to have a contamination. So this is extension of the problem we did in class when we were discussing first time when I did mass balance calculation. We did it with wet water saturated soil. This is now with we did it with sediment, this is now with soil, which means that this has water and air both together. So you have to do the mass balance for all the 3 phases together, assuming no evaporation, in the sense we are not considering, see the evaporation, when we say evaporation, in this problem we are saying that there is a soil mass, there is solid and there is water in between somewhere and the rest of it is air. This is the solid. So we have phase 3, this is water, phase 2, this is air. 1. So this entire volume is filled with these 3 phases. Now we have to distribute the chemical among these 3 phases, that the mass balance has to be written. What we say no evaporation means somewhere far away there is a soil air interface. I am not assuming this evaporation, which in real cases is always happening, continuously happening, there is no equilibrium. But we, for the purposes of this problem, we are trying to look at this. Okay. Any questions on this? So tomorrow we will do the other problem, we will just go over that. Now any other questions you have, and if you have no questions, I will move on to the next topics, which is not there in the exam, but we will start instrument methods for analysis, chemical analysis. We will start one by one.